Good morning, students. Today we are going to discuss Unit 6, Session 5, that is 80387 registers and data types. So before starting with Session 5, we will briefly discuss about Session 4, that is nothing but internal architecture of 80387 and the control register and the status register of 387. So in the internal architecture, we have seen that how the coprocessor is connected with the main processor, and in the uh, register, we have discussed about all the bits and the condition codes, that is C0 to C3, and we have elaborated it with respect to all the bits. And in today's session, we will be discussing about the register stack and the data types. So first of all, we need to understand the need of a coprocessor. So the coprocessor is a computer processor used to supplement the functions of primary processor, that is nothing but your main processor. Basically, the coprocessor is used to perform the floating point arithmetic, graphics, signal processing, string processing, encryption, and I/O operations, and many more than that, which will be accelerating the performance or the computing capability of the processor. And the coprocessor shares the instructions basically based on its purpose. So with respect to our coprocessor, our main focus is on the math coprocessor, which is 80387 and the latter coprocessors. The 387 registers, 8 individual addressable 80-bit numerical registers organized as a stack registers. Each will be used as a 80-bit register, and we have 8 stack registers, and the top of the stack is indicated with ST0. Apart from the register stack, we have 16-bit registers, namely status word, control word, tag word, and apart from these 16-bit registers, we have two 48-bit registers containing the pointer to the current instruction and the operand. All the numeric instructions focus on the contents of these registers. That means the instruction and the operand is in the main focus, because the operation need to be performed on the operands. Data types. Basically, the coprocessor data types are signed integer, BCD, and floating point numbers. In this section, we will be discussing about these three data types, which are supported by all the math coprocessors and the main processors as well. So we'll start with the signed integer. The signed integer is nothing but the data type of the coprocessor, which is of 16 bits, 32 bits, and 64 bits. 16 bits is also known as a word, 32 is known as a double word integer, and a 64-bit is known as a quad word integer. The positive, as we are dealing with the signed integer, we need to be aware whether a number is a positive number or a negative number. A positive number is indicated by a most significant bit, that is leftmost bit. If the leftmost bit is 0, then the number is indicated as positive, and if the leftmost bit is 1, then the number is indicated as the negative number. The integer word is ranging from minus 32,768 to plus 32,767, whereas double word integer ranges from plus 2 into 10 raised to 9 to, minus 2 into 10 raised to 9 to plus 2 into 10 raised to 9, and quad word integer ranges from minus 9 into 10 raised to 18 to plus 9 into 10 raised to 18. And these data types are stored in the memory with the help of the following directives, that is DW, DD, and DQ. DW is nothing but a defined word, DD is a defined double word, and DQ is defined quad word integers. As we have already used these assembler directives in our assembly level language programs, that is in our lab experiments, then we so that we are very much aware of these assembler directives. So these these data types can be represented in the pictorial form. That is, A represents a word which is of 16 bits, and the leftmost bit S is indicated as the sign bit. The B indicates a double word which is represented as short, which is of 32 bit, and the leftmost bit is a sign bit, and the long is nothing but a quad word which is represented from 0 to 63, and the leftmost bit S is a sign bit. Next data type is a binary coded decimal. Each number is stored in 18 digit packed integer in 9 bytes of memory as 2 digits per byte. The 10th byte only is a sign bit for 18th digit signed BCD number. So BCD requires 80 bits in the memory, which is represented in the following diagram, where it ranges from 0 to 79, and the leftmost byte, which is represented as sign byte, and the remaining is D0 to D17, which represents the data bits. Note that the positive and the negative number are stored in true form, that is nothing but in the decimal form, and it is never a tens complement form. Basically, the signed integer in the signed integer, the negative number is stored in the two's complement form. So it's nothing like that in the with respect to BCD. It is just in the true format of the negative number, and the assembler directive DT is used to represent a BCD data in the memory. Floating point number. Floating point numbers are oftenly called as real numbers because they hold signed integer, fractions, and mixed numbers. Floating point numbers written in scientific binary notation and have three parts. So I would like to elaborate the scientific binary notation. Basically, the scientific calculations are the large calculation on I mean, the calculation of large numbers, which is a complex calculations. So these complex calculations can be minimized by using the floating point numbers. That is, the numbers are converted to floating point, and they are normalized so that the calculation will become very easier. So basically, the math coprocessor uses floating point number because it becomes very easier for the processor to perform the complex operations. So Intel supports three types of floating point numbers, that is single, which is of 32 bits, double, 64 bits, and temporary, which is of 80 bits. Single is nothing but single precision, double is nothing but double precision, and temporary is nothing but extended precision, which can be pictorially represented as follows. A indicates a short, that is single precision, which have three parts: fraction, exponent, and the sign bit. The 31st bit is the sign bit. Whereas B represents the double precision, which is of 64 bits, and the which again it has three parts. From first 52 bits, which represented as fraction, and bit 52 to 62 represents exponent, and the 63rd bit represents the sign bit. Whereas in double precision, extended precision, it is represented in 80 bits. The first 64 bits are represented as fraction, and the leftmost bit of the fraction is always 1. The exponent is of 64 to 78, and the 79th bit is nothing but the sign bit. So these floating point formats we have discussed in computer organization and architecture in the first unit, where we have already performed the numerics based on the normalizing and denormalizing. So the following uh, steps are like this, which is converting from a decimal number to a floating point number, which can be accomplished by the following four steps. That is nothing but converting the decimal number to binary, normalizing the binary number, calculate the biased exponent, and store the number in the floating point format. So to do all these, we need to apply a few numbers. That's nothing but the number is stored, the number 0 is stored as all zeros except for the sign bit. That is here in this representation, we can have a plus 0 and a minus 0. The sign bit, if the sign bit is 1, then it indicates a negative 0. If the sign bit indicates 0, then it indicates the positive 0. So, friends, so we have already, in yesterday's table, that is condition code table, we have discussed about positive 0, negative 0, positive infinity, negative infinity, not a number, and all that. And the plus and minus infinity is stored as logic ones in the exponent with a significand of all zeros and the sign bit that represents plus or minus. NaN is nothing but not a number, is an invalid floating point result with all ones in the exponent with a significand that is not all zeros. Now we'll be converting from floating point number to a decimal number. First, in the first step, we are separating the sign bit, biased exponent, and the significand. The second step is converting the bias exponent into a true exponent by subtracting the bias. The third step is write as a normalized binary number, convert it to a denormalized binary number, convert the denormalized binary number to a decimal number. Here, the terms normalized and denormalized means moving the decimal point of a fraction, decimal point of a floating point number is nothing but normalization and denormalization. If we are normalizing a number, the decimal point is moved towards the exponent, that is towards its left. When we are denormalizing it, the decimal point is moved towards right. The floating point number can be stored in memory with respect to Microsoft assembler, that is MASM, where it has a problem that the positive number cannot be represented with a plus sign. That is, here we have given an example of plus 92.45, which must be written as 92.45 for the assembler to function correctly. And this problem has been corrected in the version 6.11 of MASM. So friends, that's all for today's session. Thank you. I hope you have understood all the uh, points which we have discussed today. The points which we have discussed today is need of coprocessor, the registers of 80387, and the data types of 80387. And the data types are nothing but signed integer numbers, BCD numbers, and floating point numbers. Thank you.